right, we're going to be reviewing the test. Real quick. You might notice that there is no corrections as to how to do it right. So what I do is I like to go over the exam, show how to do all the problems. Instead of just writing on each exam, I like to go in full detail on how to do the problems. Okay, so without further ado, let's go over the exam. I do this as a service to my students. I don't have to do this, but I do this so that you guys can learn quickly and not have any gaps in your knowledge for moving on in the semester. This is a way to try and prevent the loss of more material. So this is what I was looking for. So I was looking for on problem number 1. Okay. Clearly this is approximately this, right? But technically 13 plus an omega technically is larger than just a 13. Although they're approximately the same if we want to get into the nitty gritty. Okay. So then we move on to number 2. This is approximate these to first order. The first order, this is on a higher level than that, so we just get this. Approximate to first order. This is on a higher level than that, so this part just goes away. And we have something weird like this. Something weird. Something weird to test your knowledge. Which one's on a higher order?
0.122.
Why?
Because 0.123, like it's like higher, like it's a larger number than 0.122. And like whenever we're like comparing the little omegas, if it's a larger exponent, then that means that it's in a lower level.
Yeah, the larger the exponent of little omega, the lower level it gets. So this exponent is larger than that exponent, meaning this number is smaller than that number in terms of levels. It's on a lower level. So this approximates to this. First order. The second order, of course, it goes to 0. Okay. Over here we have omega to the 7 over 4 plus omega to the 4 over 6 minus omega to the 4 over 3. What about these guys? You didn't have to do it like this, but this is one way to see it. If you plug it into decimal representation. So it's a first order approximation. Which one goes away? As per before, the one with the highest power is on the lowest level. So this is the highest power. So that goes away when you approximate it to first order. That's kind of what we were looking for. That's the 2 omega to the 2/3 minus omega to the 4 halves. No, not 4/2, 4/3. Okay. And this is all on the recording, so you'll be able to rewatch this. I'm going to erase everything, but you can watch the video and pause it. Make sure you have everything recorded. All right, so we have this function. And we wanted to know what is f of plus capital omega. That's equal to okay. So what's inside this absolute value is an omega plus a capital omega minus 2. Is this greater than, less than, or equal to 0?
Greater than.
Yes. This is greater than 0. So by definition of absolute value, that's what we get. Down here, this is what we get here. Okay. So what happens here? We look at all of these. Up here, approximately the highest order value is this capital omega. Down here, the highest level value is an omega squared. So that means you get omega over an omega, which equals 1. Technically, it's going to be plus or minus 1 because this is plus or minus omega, but let's assume we're taking the principal square root. It's technically plus or minus 1. I will accept 1. Because typically, when people take the square root, they take the principal square root. This one looks very daunting, but really it's not that bad. Notice that the square root of x is equal to x to the 1/2. Notice that the square root of the square root of x is equal to the square root of x to the 1/2, which is equal to x to the 1/2, all raised to the 1/2 power. When you raise a power to a power, powers multiply. Do this process again, and you get this is x to the 1/8, because you'd get a 1/2 times this, which is 1/8. That equals 1. About C, we have f of x, x cubed. We want to know what is f of 1 plus an omega. Equals 1 plus an omega cubed. That's equal to 1 plus 2 omega plus omega squared, 1 plus an omega. equal to 1 plus 2 omega plus omega squared plus omega plus 2 omega squared plus omega cubed. So the problem asks you to approximate and render the real result. So when we get that, we notice we render the real result 1. I know I made all of them equal 1. It's to make you think, am I doing this right?
I kind of know.
Should all of them equal 1? That seems suspicious. I don't know if I did that on purpose, subconsciously or not, but it just ended up happening. And I thought to myself, well, maybe it might confuse them. Maybe they might doubt themselves. And I thought, well, that's what a test is.
I actually thought I got them right. Like whenever they all equal 1, I was like, maybe he like made it on purpose.
Oh, really? Yeah. Mm-hmm. Okay. Don't count on the pattern repeating, but it might not. So it says calculate this limit. This is quite simply equal to y. Why can't I just plug in a 0 into that function?
Because you're not going to get another sign.
Huh?
Because you're not getting on the sign.
No, that's not correct. It's because this function is a continuous function. Because it's a product of two continuous functions. It itself is a continuous function. And so a continuous function is, if f of x is continuous, then the limit as x approaches b of f of x by definition equals f of b. So we could just plug in the limit value into the function assuming that it's continuous. That's why you can do it. You couldn't do that unless it was continuous. What about this one? Well, we can notice that we can factor this. Cancels. So then that means this is equivalent to the limit. X approaches 2 of x plus 2. This is a linear polynomial function, so it's continuous. The answer is 4. About this one, this one's going to require a little bit more work. This is equal to f of 4 plus an omega. Okay. But that is equivalent to 4 plus an omega minus 4 quantity squared square root of 2 times the 4 plus an omega plus the 1 and the square root minus the 3. So this becomes, these cancel. So this becomes this omega squared. Down here, we distribute that 2, and that becomes an 8 plus a 2 omega plus a 1, and the minus 3 is out here. This becomes an omega squared. All over this becomes a square root of 9 plus 2 omega minus a 3. We can't approximate this to be 0 because then it violates the approximation principle, and furthermore, it's dividing by 0. So let's not go there. What we can do is multiply top and bottom by a fancy number 1 called the radical conjugate. This gives us, let's move it up here, give me some more room. Omega squared times the quantity, square root of 9 plus 2 omega plus 3, all over 9 plus 2 omega minus a 9. That's what happens when you FOIL these two, or distribute. Cancel, cancel. Now we have a omega squared up here times the quantity square root of 9 plus 2 omega plus 3, all over 2 omega. Cancel, cancel. This equals an omega times 9, or times the square root of 9 plus 2 omega 3, all over 2. So what do we get here? We can approximate, or we can send the omega through. There's many ways of doing this. This is the same thing as an omega over 2 multiplied times what's in there. And there we can actually approximate that to 9, square root of 9 plus a 3. So this ends up becoming omega over 2 times a 3 plus a 3, which is a 6. This becomes a 3 omega. Which actually, we're not done yet, because I asked you to render the real result. So that's your final answer. Determine if the following are continuous. If they're not continuous, state what kind of discontinuity they have. At x equals 0. Well, what is f of 0? That's cosine of 1 over 0. This is equal to cosine of undefined. That doesn't work. What is the limit? X approaches 0 of this. About the transfer principle. Even for omegas here. This is true. Because notice that this is the same thing as f of 0 plus an alpha or an omega, whatever. This becomes a cosine of 1 over 0 plus an alpha. It's the same thing as cosine of 1 over alpha or an omega. Really doesn't matter. We'll just leave it at alpha to keep it general and arbitrary. So what is the limit?
Zero, or I don't know.
It's not 0.
It's between though.
It's between -1 and 1. Yeah. So which one is it? Oh, no, try it again. There we go. So before, you'd have something like an x here, and you'd be able to say, oh, start here and then multiply both sides by x, and then use the squeeze theorem, or x or alpha in this case. And then you could use a squeeze theorem you can say, oh, the limit as negative x approaches 0 is a 0. The limit as x approaches 0 is 0. So that means the limit as this function approaches 0 is 0. But you can't say that about this function because there is no x here. So the limit does not exist. So what kind of discontinuity is it? It's not a jump discontinuity. It's not a removable discontinuity. What other kinds is there? It's not an infinite discontinuity. As you approach 0, the value oscillates between -1 and 1. So this is a oscillating discontinuity. I believe that's in your book. I believe oscillating discontinuities were in your book. It means that the function jumps up and down in value because cosine is going between -1 and 1.
Oh,
It's oscillating.
that's the one where you scribble a lot before you get to it, but you don't get to it.
That's right. That's right.
I didn't put that in the book.
That's right. Excellent. Excellent. That's correct. So then, okay. Well, f of 1 is equal to this. It's undefined. But what is the limit as x approaches 1? These cancel. These cancel. Factor out an alpha in the numerator. Those alphas cancel. So this approximates or renders the real result. √2. And it's true for positive alpha or negative alpha. So it equals square root of 2. So it doesn't evaluate, but it does have a limit. Could we not define a function capital F such that this function is piecewise defined and the equals are f of x, x is not equal to 1, and the limit value square root of 2 if x equals 1? Could we not construct a continuous function capital X like this? So it is a what kind of discontinuity? It's a removable discontinuity because through this trick we could remove it. Prove that all quadratic functions are continuous, i.e. prove that all functions f of x of the form a, x squared plus bx plus c are continuous at some arbitrary x is equal to k. If it's continuous, that means the limit as x approaches k of f of x should equal f of k. So if we prove this, we're done. So let's actually take a limit of f of x. Well, by definition, that's f of k plus alpha. And that's a times k plus alpha quantity squared plus b times k plus alpha plus c. This is equal to a times the quantity k squared plus 2k alpha plus alpha squared plus bk plus b alpha plus c. This is equal to ak squared plus 2ak alpha plus a alpha squared plus bk plus b alpha plus c. You can render the real result by retaining everything that doesn't have an infinitesimal term in it. Go away, go away, go away. Notice that what remains is ak squared plus bk plus c. And this is precisely f of k. That's what we get when we replace x with the k. Oh, well, just these two guys. So cha-chink, it's continuous. And since x equals k is an arbitrary element of the real numbers, it's continuous for the whole reals. Is this function continuous? Said explain your reasoning. I was hoping that you said it's continuous on a specific interval and on a specific restricted domain, not the full real domain, but a restricted domain. How do we find said restricted domain? Is by getting this denominator here and saying, oh, I can't let that ever equal 0 because then we'll be dividing by 0. If we can make sure we don't ever divide by 0, then this is a polynomial divided by a polynomial, so it's a rational function, and rational functions are continuous on their domains. So if we can figure out when is this never equal to 0, we're good. We can notice that this factors into this. Two numbers that add to give you 7, but multiply to give you 12. It's 3 and 4. Notice that that trick only works when this coefficient is 1. We call that a monic polynomial. So then this implies that x plus 3 cannot equal 0, and that x plus 4 cannot equal 0. These simultaneously imply that x cannot equal -3, x cannot equal -4. So your domain is -infinity all the way to this guy, -4, union -4 all the way to its close neighbor, -3, union -3 all the way to positive infinity. On this domain, your function is continuous because it's never dividing by 0. That's the only thing that could have gone wrong in this function. There's no square roots, so there's no imaginary numbers involved. It's only division by 0 that we'd have to be worried about. That's the kind. I wanted you to say that. I wanted you to explain your reasoning like so. Find the limits. Limit as x approaches pi over 4, sine of x over x. Continuous function because it's trigonometric function. Continuous function because it's a linear polynomial. So you just plug it in because it's continuous. So this becomes √2 over 2 divided by pi over 4. It becomes square root of 2 over 2 times 4 over 5. It becomes 2 square root of 2 over 5. limit as x approaches 0 from x to the 15th minus 13x to the 6th is 2x squared minus 10x plus 5. This is a polynomial, so it's continuous. So that when you take the limit, all you got to do is plug in 0 for all the x's, because you know it's continuous. If you didn't know it was continuous and you tried to, it would be horrific. So it just reduces to 5, because you plug in a 0 for all the x's, so all these terms go away. Limit x approaches pi, tangent of x. That's just tangent of pi. That's sine of pi over cosine of pi. That's -1, and on top it's 0. So the whole thing is a 0. Find the equation of the tangent line to the function at. Okay, so m is equal to f of alpha plus 4 minus f of 4 all over alpha. That's what the slope is defined as. So then this equals okay. Now what? You just say that's square root of 4 minus square root of 4? All over alpha? No, because it violates the approximation principle. Oh, can just be called 2. This can be called 2. So this ends up becoming 4 plus alpha minus a 4, all divided by alpha times the quantity, square root of 4 plus an alpha plus a 2. Cancel these, move the calculation upstairs. This becomes alpha in the numerator times this alpha times the quantity, square root of 4 plus alpha plus a 2. Cancel out the alphas. So then this is just 1 over the square root of 4 plus alpha plus a 2. Which approximates, now we can do it to 1 over square root of 4 plus 2, which is equal to 1 over 2 plus 2, which is equal to 1 over 4. So that's our slope m. We need a y minus y1 is equal to m times x minus x1, and we need one point. We need a slope and a point. That's why this is called point slope form. The way we get the point on this function is say, oh, if x equals 4 is on the function, then f of 4 is on the function. So our x1, y1 is equal to some 4 comma f of 4. But this is equal to 4 comma square root of 4 equal to 4, 2. So then this equation becomes y minus 2, which is equal to our slope 1/4 times x minus our 4. So this becomes 1/4 x minus 1. And when we add a 2 to both sides, that implies we get y is equal to 1/4 x plus 1. Here's our equation. an electron is ejected out of a radioactive iodine atom, position function. Find the instantaneous rate of change of the velocity at time is equal to 2. Okay, so velocity, v of t, is the change in your position function. It's your f of alpha. So v of 2 is your f of alpha plus 2 minus your f of 2 all over your alpha. If we get to it today, you'll see that this is intimately related to the derivative. So notice that this becomes alpha plus 2 cubed plus alpha plus 2 squared minus 1 minus 2 cubed plus 2 squared minus 1. Everything divided by an alpha. Bring this over here. So we have alpha, bring it over here, we have alpha squared plus 2 alpha plus 4 times alpha plus 2 plus alpha squared plus 2 alpha plus 4 minus a 1 minus an 8 plus a 4 minus a 1, it's a 12 minus a 1, 11. So this becomes 11. Everything is divided by alpha. So then this becomes alpha cubed plus 2 alpha squared plus 4 alpha plus 2 alpha squared plus 4 alpha plus 8 plus alpha squared plus 2 alpha plus a 3 minus an 11. Everything all over an alpha. 3 plus 8 is, yeah, it's 11. I can cancel out these. I see a 4 alpha here, a 4 alpha here, 2 alpha here. That becomes 4 plus 4 plus 2, which is 10 alpha. So this becomes 10 alpha. I see a alpha squared term. This becomes 4 plus 5 alpha squared. Plus this alpha cubed that's remaining all over alpha. We can factor out alpha from the numerator. So this becomes alpha squared, or alpha times alpha squared plus 5 alpha plus 10 all over alpha. Cancel those out. Okay, so then what's left is alpha squared plus 5 alpha plus 10. Okay. Let's see here. So that is your let's see here. That's your V of 2. Okay. What happened here? Okay. Alpha squared plus. Oh. Yeah. Well, what I should have done is instead of alpha, I should have left it as a T. Okay. And kept this an alpha. So everything upstairs should have a T in it instead of an alpha. Okay. It's just a notational thing. So over here, we would rewrite this right here, not the factoring. This would have been 10t plus 5t squared plus t cubed all over alpha. Hold up here. Yeah, I'm gonna do this again because this is annoying. I'll do it all over again because I don't want to confuse you guys. Okay, I'm sure you guys know how to do it, but for the sake of being thorough, I want to show you how to do it. I shouldn't have done it the way I did. Okay, so the velocity, v of t, in general, is f of t plus alpha minus f of t, all over alpha. It's the same thing, just not with the 2 that I plugged in for t, okay? Then once you figure this out, you can find what v of 2 is. This is what we want to know, okay? But keep it general. This becomes this, t plus alpha right here, cubed plus then this just becomes t cubed plus t squared minus 1, everything divided by alpha. Okay, so this ends up becoming t squared plus 2t alpha plus alpha squared times t plus alpha plus squared plus 2t alpha plus alpha squared minus 1 minus your t cubed minus your t squared plus 1, everything over your alpha. So then this becomes, I'll move this over here. So this becomes a t cubed plus 2t squared alpha plus t alpha squared plus t squared alpha plus 2t alpha squared plus alpha cubed plus your t cubed, or plus your t squared plus 2t alpha plus alpha squared minus 1 minus t cubed minus t squared plus 1, everything over alpha. Okay, so now the 1's cancel. The t cubes cancel. The t squared alpha term, here's a t squared alpha. Here's a t squared alpha. Are those our only 2 t squared alpha terms? Yep. So they combine to give us 3t squared alpha, and we can get rid of them because we added them. So what about our t alpha squareds? Here's a t alpha squared. Here's a t alpha squared. Do we have any more t alpha squareds? Nope. So then these combine to give us a 3t alpha squared, and we can get rid of them. Okay. So what about our alpha cubes? There's just one alpha cube, so we write that. That goes away. So what about our t squared? T squared is right here, negative t squared is over here, so they cancel. What about our 2t alpha? A t alpha term. That's the only lonely t alpha term, so plus 2t alpha. And alpha squared, it's just a lone, everything divided by alpha. Okay, it's rearranging and combining. So now we could factor out an alpha and cancel. So once we do that, everything is reduced by an alpha, and then there's no longer an alpha in the denominator. So this becomes 3t squared plus a 3t alpha plus an alpha squared plus a 2t plus an alpha. Okay, so then you can render the real result. Everything that doesn't have an alpha in it goes away. I mean, everything that does have an alpha in it goes away. And everything that does not have it remains. This is your v of t. Okay. The question asks us, what is v of 2? So v of 2 is precisely plugging 2 in for t for that function. So it's just 3 times 2 quantity squared plus 2 times 2. This ends up becoming 3 times a 4 plus a 4. This ends up becoming a 12 plus a 4. This ends up becoming a 16. If you're going to do something, do it thoroughly. That was it being done thoroughly. I plugged it in for, I was doing it not wrong, but I plugged in a 2 for the t. And I wanted to show you guys it in general for arbitrary values. Because once you get that function, you now know it for all possible inputs. You know v of 2, you know v of 8, you know v of 36. You might even go v of -5. Because if the function translates to the electron's behavior backwards in time, then you could be able to calculate its velocity backwards in time. Bonus 1. You got a function like this. We have x equals 1. What kind of discontinuity does it have? I already gave you a hint because I was feeling generous. How many bonus did I give you? 3? Yeah, that's a lot. What kind of discontinuity is this? Well, f of 1 is equal to 1 over 1 minus 1, which is equal to 1 over 0, which is undefined, really. What is the limit as x approaches 1 of this? Well, it's equal to 1's cancel. It's just 1 over alpha, which is equal to capital A. So this really implies plus or minus infinity, right? So it has a plus or minus infinity discontinuity. Bonus number 2. Construct a function that would fix this and make it continuous. So the function looks like this, right? It's got a vertical asymptote at x equals 1. So the function is going to look something like this. Let's put it in yellow. It's going to look like this. So how can we fix that yellow function? Make the asymptote go away. Define the function at the asymptote to equal some c. Let this be some function c. Then what used to be a vertical asymptote now looks like this. I know what you're thinking. Is that legal? Does it obey the vertical line test? Is it a function anymore?
Yeah.
It is? Why is it a function? Doesn't it look like it's disobeying the vertical line test?
Oh no, because it's like infinitely like getting closer, but not like in the same place.
Really, this is up to interpretation. What I will say is this function here is not differentiable here, meaning it has infinite slope, meaning that It's not differentiable. We'll talk about differentiability on Wednesday. But is it continuous? It could be. If anybody, for everybody who attempted this, I gave them points. This was one of those like throw it in the air kind of questions. Okay. So is this disobeying the vertical line test? Is it? It visually looks like it is, but is that visual a true representation of what's going on? Every time we zoom in, this looks like a vertical line, but if we zoom in enough, to this little spot, zoom in far enough, and you might see that, oh, it doesn't look like a vertical line, it's actually like a curve when you zoom in far enough. Then it locally, at the small scale, it's not disobeying the vertical line test. No, you know, I say, don't worry, this stuff won't be on your test. It ended up being on your test, but as a bonus point, I just want to see what you guys would say. This was a problem that went beyond your scope, but I asked it anyways because I think you guys are capable of it, every single one of you. Okay, last one. I know we're probably over time. Yeah, about 4 minutes over. What is the slope of the tangent line to this function at x equals 2? Again, m is equal to f of 2 plus alpha minus f of 2 all over alpha. So this ends up becoming 2 plus alpha cubed minus 2 cubed all over alpha. Okay, once you work that stuff out, you get alpha cubed plus 4 alpha squared plus 4 alpha plus 2 alpha squared plus 8 alpha plus 8 minus the 8, everything over alpha. When things cancel, you end up getting alpha squared plus 6 alpha plus 12. And this renders the real result 12. Okay. That's it. Everybody who does the homework gets 100. You turn in your homework, you get 100. So 30% of your grade is given if you put in the effort in here. The tests are worth 40%, right? What else is there? Wait a second. No, the tests are worth more than that. If there's just homework and tests,
The final.
yeah, the final is like its own thing. The midterm exams are worth 40. Homework is worth 30. That leaves the final exam to be worth a huge chunk of 30. So what will save you in this class is continuing to work hard on your homework, asking questions, and yeah, you don't get feedback on the homework, but you get complete solutions to the homework. So do it on your own, see how your problems match up to that. If you don't get why your solution isn't looking like the solutions there, then you need to ask me or ask a colleague who does understand. Okay, go to your other classes because you might be late. If you need me to email one of your professors to tell them, hey, this student was late because I ran class late, let me know. Something like that happens, I will make sure you guys don't get in trouble. Okay? Yep.